Good morning, Townview. Welcome back to Chemistry Online.
All right, y'all, let's go ahead and get started. So today we're going to be talking about radioactive decay. So when I say decay, what do you guys think about? What is decay? Can anyone tell me when you hear the term decay, what do you think about? Okay, decomposition, good. So think about like if you have a tooth and you're undergoing tooth decay. What is tooth decay? All right, so first you get a tiny cavity, you don't take care of it, it becomes a larger cavity and a larger cavity. And basically it's just the breakdown of the tooth. That's what decay is. So elements, they undergo decay. So why do elements undergo decay? So the short answer is they all want stability. So let's talk about how that works. So over here at the top, we have uranium-238, which is a radioactive material. And uranium-238 has a half-life of 4.5 billion years. So if I start with 100 grams of uranium-238 and 4.5 billion years later, how much uranium-238 am I going to have left? All right, so half-life tells us that we're going to have 50 grams left. So half of it is going to turn into something else. Half of it will still be uranium-238. And then 50 grams are going to be thorium-234. Thorium-234 has a half-life of 24 days. So in 24 days, how many grams of thorium am I going to have left? 25 grams, good. How much protactinium am I going to have? 25 grams, good. So protactinium has a half-life of about 1.5 minutes. So in 1.5 minutes, how much protactinium will I have left? Okay, 12.5, good. How much uranium-234 am I going to have? Also 12.5, good. And what you're noticing is every time it undergoes a half-life, half of it is going to turn into something else, half of it will stay that thing, and it's just going to keep going through that half-life. Eventually, it's going to reach lead-206. So once it reaches lead-206, that's when it's found its stable point. And once it's stable, it's not going to change anymore. So take a look at my periodic table real quick. Here's lead right here. There's lead. Everything after lead, so everything after 82, wants to be just like 82. So once it reaches 82, that's when it's not changing anymore. At that point, it's stable, and that's the end goal for everything. So why do elements undergo radioactive decay? They're looking for stability. So think of it like a little kid, like a 3-year-old. You just gave him like a lollipop and a big bag of M&Ms. What are they going to do after they've consumed the M&Ms? They're just going to run. No, they're not going to go to bed. They're just going to run around and try to burn off that energy until the energy is gone. Once the energy goes away, that's when they go to bed. So radioactive decay is just a way of reaching stability. Now, this part you don't need to write. It's just something I kind of want y'all to understand. So what makes an atom stable? Let me pause real quick because I would like to show y'all an illustration of this. All right, so we're going to build an atom real quick. So we're going to take, I'm going to take 3, actually no, we're just going to put 6 in here. So we're going to make a carbon atom. And then carbon 12 is going to have 6 neutrons. That's 1, 2, 3, 4, 5, and 6. And I don't care about electrons. I'm not going to put any electrons in there. But you can see that right now our carbon is stable. I throw in another neutron. It's still stable. I put in one more. And what ends up happening? Actually, it wasn't showing stability. So let's remove some of these neutrons. We're going to take it back to neutral. And then we're going to hit show stability. That way it tells us if it's stable or not. So then we add one more. It's still stable. We make it carbon 14. Now you can see that it's unstable. And if you're trying to make an element unstable, all you have to do is add neutrons to it. Doesn't matter what that element is. If you add neutrons, additional neutrons are what make elements unstable. So here's boron. So this is boron with 6 neutrons, and it's going to be stable. You add in another neutron, and it becomes unstable. So what makes an element unstable? Too many what? Too many neutrons. That's what makes them unstable. So ideally, an element wants to have a 1-to-1 ratio of protons to neutrons. So for every 1 proton, it would like to have 1 neutron. That's what makes small atoms neutral. Now, for larger atoms, that ratio is going to be closer to 1.5 to 1. That's not something I want you guys to know or remember. I just want y'all to have an understanding of what makes elements stable versus unstable. When they have a really close ratio of protons to neutrons, they're stable. When they have way more neutrons, that's when they're unstable. All right, let's keep going. So types of decay. So on your paper, I want you to write types of decay. We're going to discuss 3. I'm actually going to go over like 6 of them. Only 3 are tested. So those 3, I'm going to have y'all focus a little bit extra on. So types of decay, the first one we're going to discuss is called alpha decay. And the symbol for alpha decay is just going to be a lowercase a. That's alpha decay. And alpha decay is when an atom loses an alpha particle. And an alpha particle is made up of 2 protons and 2 neutrons. What else is made of 2 protons and 2 neutrons? A helium, good. So if you look at the periodic table, you're going to see that helium has 2 protons and 2 neutrons. That's what makes up a helium. So when something undergoes alpha decay, it's releasing helium particles. We'll talk about how there's a change in mass in a minute. Here's an example right here. But on the next slide, I'm going to show you how the mass of an atom changes once it loses an alpha particle. But another thing I wanted to discuss is, does anybody know where in the world we get most of our helium from? Well, not really, because we have the atmosphere. That protects us from all things outside of the Earth. So the helium we have on Earth, it's already here. But where do we get our helium from? Anybody know? What is it? Not really. All right, so we drill for helium. So anywhere you drill and you get natural gas, anybody know how we get natural gas out of the ground? I'm going to put natural gas just because NG is not a thing. How do we get natural gas? Anybody know the type of drilling process? What's it called when we put a tube in like this? All right, so this is fracking. And this is different. This is different from regular drilling because when we drill normally, we're drilling for liquid oil. When we do fracking, that's when we're trying to get out natural gas. When we say natural gas, we're not talking about any particular type of gas. There's a lot of different gases in there. There's CO2, there's CO, there's methane, there's ethane, there's all types of gases in there, propane. All of these are in natural gas. So if your stove runs on natural gas, is there only one type of gas going into your stove? No, it's getting a large combination of gases. That's what natural gas is. If you have a propane grill, what type of gas is going in your grill? Propane only. So propane is one of the gases that's in natural gas. Anyway, so here where you get natural gas, you also get radioactive gases like neon, argon, krypton, and also helium. Okay? So helium, we capture it in natural gas. So when we get this large selection of gases, we distill these gases and we separate them, and that's where we get our helium from. The whole point of this is I wanted to tell y'all, anywhere we can find helium, directly underneath that helium, you're going to find uranium. Because what does uranium do? Uranium, it undergoes alpha decay, and alpha decay is just the release of alpha particles, and these alpha particles, they get caught in these chambers, and they are the helium. Okay? So anywhere you have helium, you have uranium underneath, and that uranium is undergoing alpha decay, and that alpha decay is the helium that we capture and end up putting in balloons and stuff. There's a lot of uses for helium. That's just one example. All right, let's keep going. Don't worry about this stuff. I'm going to give you a paper that's got all this. But here's what we're going to focus on today. I want to focus on the math. So here we have an image. So we got some plutonium, plutonium-240, and it's about to undergo alpha decay, which basically means it's going to lose an alpha particle, which means it's about to lose the mass of a helium. It's going to lose 2 protons, 2 neutrons, and it's going to become uranium-236. What this looks like in a mathematical form, in a mathematical equation, is like this. So everybody take a look at my screen. So here we have polonium, and it's got a mass of what? What's the mass of our polonium? 210. Over on this side, we have lead, and we know that lead is stable. So once polonium undergoes alpha decay, it becomes stable. So our lead, so here our mass is 206 plus 4. So what's the total mass on this side? It's got a mass of 210. And then what's our total atomic number on this side? 84. That's it. That's what alpha decay looks like in a mathematical equation. So I'm going to clear this so that we can do it again. So over on this side, our mass number should equal what? 210. Our atomic number should equal what? 84. So both sides need to equal each other. All right, so I'm going to give you guys 4 laps. I want you to answer these 2 real quick in your journal. What you're trying to do is fill in these blanks. You already know this is alpha decay, so just go ahead and fill in the blank. Tell me what element goes there. All right, let's take a look at this one real quick. So we already know this is alpha decay. How do we figure out the mass that goes here? Okay, we subtract. Good. So 222 minus 4, what does that leave us with? 218. And then how do we figure out the atomic number over here? All right, 88 minus 2, what does that leave us with? All right, we have 86. Now we look at the periodic table. What element has 86 protons? Radon. So this is going to be radon. And that's it. You're done. Hands up if you got this. Okay, good. Go ahead, solve the next one. Okay, so now it tells us what we're ending up with. So it's telling us what our product is. It's also telling us that we have an alpha particle. So how do we figure out the mass on this side? What do we do? All right, so this time we're going to add. So 199 at the top. What goes to the bottom? And then what element is this? All right, and that's it. Now, another thing I wanted y'all to recognize from here is an alpha particle could be drawn out like this, where it shows you the alpha symbol, or they could just write a helium. So anytime you see a helium atom on the product side or an alpha particle on the product side, what type of decay are you looking at? That's going to be alpha decay. Any questions on this? All right, we'll talk about strength in a little bit, but so far all I want you to know is how to solve the math. All right, so the next type of radioactive decay, this is the confusing one, or the one that confuses people the most. This one is called beta decay, or positron emission. You guys are just going to call it beta decay, though. So ignore this one. You're just going to call it beta decay. The symbol for beta decay is just a B with a mullet. Looks like that. All right, so there's 2 types of beta decay. We have beta minus, and then we have beta plus. So the difference is in beta plus, I'm gonna zoom in so that we can see these. I can't really draw when I zoom in, but I want us to see these up close. So if we look at my screen, I'm going to use a laser pointer. Oh, it won't even let me use laser pointer. All right, so I can't really touch the screen when I zoom in. But I want y'all to take a look. So looking at the carbon, what's the mass on the carbon? What's the mass on the nitrogen? So after beta decay, does the mass change? No. Does the number of protons change? Yes. Does the number of neutrons change? Yes, it does. So protons goes from 6 to 7, and then neutrons goes from 8 to 7. Looking here at the bottom, this is beta plus. In beta plus, is the mass changing? We're going from carbon 10 to boron 10. Is the mass changing? No. Is protons changing? Is neutrons changing? Yes. All right, so I'm going to zoom out so I could draw this stuff for you. All right, so you don't need to know about antineutrinos, and you don't need to know about neutrinos. You also don't need to know about positrons. But here's what's actually happening. So in beta minus decay, you have a neutron, and your neutron basically has a positive charge, and it's got an electron in it, and that's what makes it neutral. You have a positive charge, and you have an electron absorbed into this positive charge, and that's what creates this neutron. Now, what it does is it releases an electron. That's this electron right here. When it releases the electron, what does this neutron become? What does it become? It becomes a proton. So a neutron becomes a proton in beta minus decay. So the neutron gives up an electron, that's this electron right here, and then it becomes a proton. That's why we have 7 protons now. And when it goes from 6 protons to 7 protons, are we looking at the same element, yes or no? No, when you change number of protons, your element changes. So in beta decay, there's always a change in what element you're looking at. Now over here, this one is even more confusing. So a neutron here, so here you have a proton, and here's our proton. A proton just has a positive charge. What's happening is the proton is releasing the positron, and a positron is basically the same as an electron. This is something you only witness in nuclear, which is why we've never talked about positrons before. But basically, when a proton gets rid of its positron, it becomes neutral. So it's not like a neutron that has a positive charge and a negative charge. It's just a proton with a positive charge. it loses its positive charge. And when it loses the positive charge, your proton turns into what? It turns into a neutron, okay? Now, you don't need to remember any of that. Here's what you need to remember. When you see an electron on the product side, what kind of decay are you looking at? You're looking at beta decay. You don't need to know beta plus. You don't need to know beta minus. You just need to know beta. So let's take a look at what the math looks like. So a beta particle, let's write this down. A beta particle is just an electron. Or it's a positron, which is the opposite of an electron, but you don't need to know that. So a beta particle is just an electron. Bless you. You don't need to write any of this. I'm going to give you all this. All right, let's move on. What did you need? All right, so here's what the math is going to look like. So here we have carbon 14, and you can see that our mass is not changing, but our atomic number is changing. So one of our neutrons is turning into a proton. Now here's what the math is going to look like. I'm going to erase this. So what's 0 plus 14? It's 14. And then what's 7 minus 1? 6. So the math is still going to look right. Okay? Now, this could be written in multiple ways. I'm going to show you a few of the ways this could be written out. So this could say beta particle, so it could have the B with the mullet, or it could just have an E. So if it has an E, and you can see that it's an electron, that's also an example of beta decay. Now, another thing that you can see, I'll show you on the next problem. I'm going to give you 2 laps. I want you to solve this one real quick. Tell me what goes in that box. All right, so 2 laps. Okay, let's go ahead and solve this one. So looking at this side, so we have 25 over here and 0 over here. So what is our mass going to be over here? 25. And then what number minus 1 will give us this 12? So 13 goes here. And then what element is 13? Aluminum. Good. So Al is going to go here. Now, this is called beta minus, okay? Now, what's beta plus going to look like? I want to show you all beta plus over here. So if we had the same symbol, except instead of minus 1, it's going to say plus 1. So in this scenario, what is the mass number going to be? What's the mass going to be? It's still 25, but what is the atomic number going to be? What number plus 1 equals 12? And then what atom is this? That's going to be Na. And this is also called beta decay, except this is beta what? This is beta plus. You don't need to know beta plus, beta minus. You just need to know that this is what it looks like when you see it written down. So it looks like you're adding or subtracting a proton, but our mass number stays the same because our beta particles, they don't have mass. Electrons, we assume that they have 0 mass. All right, let's go ahead and move on. So our last type is going to be gamma radiation. What can you tell me about gamma radiation? What do we know about gamma? What do we know about gamma? I heard Hulk. Hulk is good. So what do we know about gamma? Bless you. It's what? It is. So it's on the electromagnetic spectrum. What else do we know about it? It is. What else do we know about it? Is it strong or weak? All right, so just like before, gamma radiation is going to be the strongest type of radiation, and it's the release of high energy photons. So anytime you see radioactive material on TV and it's glowing green, what are you actually looking at? You're looking at gamma radiation. So the green glow, that's the gamma radiation. And gamma radiation is just high energy photons. It's that glow. It's ejected from the nucleus. And what you need to know about it is usually it comes with a different type of radiation. So if you have alpha, you're also going to have gamma. Another important thing you need to know about gamma is the symbol. And the symbol is this squiggly Y. So this is the symbol for gamma. All right, let's keep going. All right, we're moving. All right, we're moving. Okay, so here's what the math is going to look like. So gamma is actually the easiest to spot because let's take a look at this. So here we have cobalt 60, and here we have cobalt 60. Is the cobalt changing at all? No. But what you're going to see is the gamma symbol. So we are releasing this gamma energy, and the cobalt is basically just glowing green. Okay? So gamma radiation, you can see it, but it doesn't change anything. So it's a release of energy. However, it doesn't change the mass number, doesn't change the atomic number. So anytime you're showing gamma radiation, I can show you gamma radiation right now. So let's do carbon 6 and then 14. Over on this side, it's going to be 14 and 6, and it's still going to be carbon, plus you're going to get the gamma radiation. So gamma just looks like this. It's the same exact thing, except there's the addition of gamma. For you guys, I told you gamma always comes with either beta or alpha. When you look at it in a math problem, it's always going to be by itself. So don't try to mix it with anything. It's always going to be solo, and it's going to look just like this. All right, let's move on. Okay, so the first question you're going to see on the ACP is everything we just covered. And the second question is going to be related to this section right here, which is all about the strength. So here's gamma right here. What do we know about gamma? This is the strongest. So they all cause cancer. Gamma causes the most cancer, the most quickly, and it's just the most powerful. Alpha is going to be here at the top. This one is going to be the weakest. So when you see people that work at a nuclear site and they're just wearing scrubs, alpha decay can be blocked by scrubs. Your clothes can block alpha radiation. A sheet of paper. So paper, I would write this down. Paper can block alpha radiation. These are the question you're going to see is going to ask you something along the lines of paper can block what type of radiation? Aluminum can block what type of radiation? Lead is needed to block what type of radiation? So alpha can be blocked by your skin. So if you're hit with alpha radiation, it's just going to bounce off your skin. Beta radiation, this one's way more harmful. For this one, you need aluminum. So aluminum can block beta decay. So if you're in your car can block beta radiation. If it can block beta radiation, can it block alpha? Yes. So aluminum can block beta and alpha. And then lastly, for gamma, this is what you need to know. For this one, you need either lead. So think about when you go to the dentist and they put on the lead coat. That lead coat is to block the gamma radiation or the X-rays. And you also need concrete. And a lot of concrete. So 3 feet of concrete. So those are the things needed to block gamma radiation. 3 feet of concrete can block a whole bunch of it. Also, a lead box can block a whole bunch of it. Who did Chernobyl? So one of my people was presenting Chernobyl, and they gave me a fact that I had to fact check because it seemed so untrue. But I fact checked them, and it turned out to be true. So here's the Chernobyl reactor, and on top of the reactor you have a lid that's basically covering the entire reactor. And over on this side it's 9 feet, and then from this side to this side it's going to be 50 feet. Okay, 50 feet, and this is concrete and steel. Okay, so 9 feet by 50 feet, and it's a circular. It's a circular. What do you call it? Cylinder. If you had to guess, how much do you think this would weigh? So 50 feet by 9 feet of concrete and steel. How much do you think that would weigh? Way more than a ton. So my thought was somewhere in the realm of 100 tons. This thing ended up being 2,000 tons. And here's what happened in Chernobyl. Once there was a meltdown, this entire lid, it blew out of the reactor and it was over here. So something that weighed 2,000 tons, so 2,000 times 2,000 pounds, that's how much this lid weighed. And it was blown off of the reactor. So when a student mentioned that this lid had a mass of 2,000 tons, I had to fact check them and it ended up being true. But this, the reason it's so heavy is because it's blocking the gamma radiation. And they did overkill. 9 feet, that's more than they needed. But they went with 9 feet anyway. And they had 4 reactors, by the way. So 4 reactors times these 2,000 ton concrete and steel. So these reactors, they cost a lot of money to build. Anyway, let's keep going. We're almost done. So you don't need to take notes here. I just want to describe these things so that you know them. So neutron bombardment, can anyone tell me what this sounds like? What is neutron bombardment? All right, so you basically throw neutrons at something. So think of it like a ray gun, okay? A ray gun, and all it does is it shoots neutrons. So anything you shoot neutrons at, you make them more radioactive. We talked about how if things have additional neutrons, they become unstable. So neutron bombardment is when you shoot neutrons at something to make it radioactive. So when we shoot neutrons on things, an example of this is creating radioactive elements. So on the periodic table, how did we make everything past uranium? What did we do? We bombarded them with neutrons. So that's how we created the neptunium and all these elements past 92 on the periodic table. So neutron bombardment, that's how we make new isotopes. Next one is electron capture. So electron capture, it looks just like beta, except the electron is on which side? Product or reactant? It's on the reactant side. So it's on the reactant side because the electron is captured and one of your protons turns into a neutron. So this one you're not tested on. I just wanted to mention it because it's often mentioned. And I usually have students write this whole thing, but you don't have to because I'm about to give this to you. All right, so just a quick fact. So the nearest reactor to Texas is to Dallas, Fort Worth, is about 50 miles away from us right now. It's called Comanche Peak, and it's pretty close. We don't need to know about the history, so you don't got to worry about this. Here's a term that I want y'all to know in case you come across it. Radioisotope is just an isotope that's radioactive. So is carbon radioactive? No, trees are made of carbon and we're made of carbon. So carbon is not radioactive. Is carbon-14 radioactive? Yes. So carbon-14 is a radioisotope. Okay? So it's a radioactive isotope of an element that's not commonly radioactive. What about uranium? Is uranium a radioisotope? No, because uranium is always radioactive. All uranium is radioactive, so it's not a radioisotope. Radioisotopes, they have to be radioactive isotopes of an element that's not radioactive. So anything before lead, if it's radioactive, it's a radioisotope. Everything after lead is mostly radioactive already, so it's not considered a radioisotope. All right, let's move on. So this was just an interesting fact. Have you ever seen those clocks that glow in the dark? So nowadays, we don't use radioactive material anymore. But in the past, if you go to an antique shop and you see a clock that looks like this and it glows in the dark, it's because it was painted with radium. And the ladies who had to paint these watches, this is what their hands look like. So the radium, it caused their hands to decay. But these clocks, if you go to antique shops, you can still buy them. And if you wear them on your wrist, this is what your wrist is going to look like. So you don't want to wear them. You don't want to buy them. You actually want to avoid them. Stay out of antique shops. A lot of radioactive material there. And then another thing is food irradiation. So a lot of the food that you guys consume has gone through gamma radiation. And the reason for that is it kills a lot of harmful bacteria and it increases the shelf life of food. If you ever buy strawberries from like the farmer's market, they go bad really quickly because they haven't been hit by that radiation. Has anyone ever bought strawberries and then they look like this, like after a couple days? Those are the ones that have not been hit by radiation. But a lot of food goes through radiation nowadays. Almost all fruit goes through radiation. When we import fruits and vegetables from other countries, we always hit them with radiation because we don't want any of their bacteria. All right? So, and that's gamma radiation, and it doesn't make the food radioactive. It just kills the bacteria that's on the food. It's safe, yes. You don't want you don't want to be hit by the radiation, but it's okay for your food to be hit by the radiation. Also, they do this to milk. It kills the bacteria in milk. All right, and last thing I want to discuss is smoke detectors. So smoke detectors, they have this material called americium in it, and americium undergoes alpha decay. What does that mean? What does it shoot? It shoots alpha particles, which are basically helium atoms, okay? So here we have our battery connected to our smoke alarm. Does anyone at their house have a smoke alarm that beeps all the time? All right, y'all got to change that battery. Do your mom a favor. So your smoke alarms, they're actually, they have electricity in them because your smoke alarms are connected to each other. So when one alarm goes off, what happens at the rest of the house? They all go off. So these smoke alarms, they actually have two sources of power. One of them is from the house, but if the house didn't have electricity, they want the smoke alarms to continue to work. That's why you have two forms of power. If the battery doesn't work, that's when it constantly beeps. It's letting you know you need to replace the backup power. Anyway, so here's how this works. Everyone look up here. You might see this real soon. So your battery, it's got a positive side and it's got a negative side. And what you've created is an open circuit. And this open circuit, it's got a americium underneath that's shooting these alpha particles going from the negative side to the alpha side. So basically, it's closing the loop. As long as this loop is closed, your smoke alarm is quiet. What's going to happen, though, if smoke goes inside of this loop? Will the alpha particles be able to cross? No. So you've created an open loop. So anytime you have smoke inside your smoke alarm, you create an open loop that causes the alarm to go off. And that's when your mom tells you grab a blanket and then you start like trying to, blow air at the smoke alarm to make it get quiet. If you have a leaf blower, that's the quickest way to do it, by the way. Just grab your leaf blower, hit it for a second, and it goes quiet. Do what? A button? No, that's the test button. That's to see if it works. Y'all don't blow at it with like a pillow or something? The button is like, that's the test button. Okay, I'm gonna have to test that because as far as I know, the button is just a test button. You press that button once a year to make sure that the battery works. But anyway, that's it. That's all I got. Actually, let's go ahead and do some practice. Okay, let's take a look at this real quick. So here is today's assignment. So here at the top, you're going to see we have some notes for nuclear. And then here's that chart that I told you guys earlier. You don't have to write down because I'm going to provide it. So there it is right there. This is also going to help with today's assignment. So just know you are not tested on electron capture, neutron bombardment. You are tested on gamma, so this one you definitely want to know. And then positron and beta, we call both of these beta, and then here's alpha right here. So it tells you what the particle looks like, its effect on atomic number, its effect on atomic mass, and whether the element changes once it undergoes that kind of decay. So all of that information is right there for you. So let's take a look at number one together. So number one, what type of decay is this? Beta, good. Why is it beta? Because it's got an electron. So over here, what is the mass number going to be at the top? What goes here? 14. And then what's 7 minus 1? And then what element is this? Carbon. Good. That's it. Let's take a look at number 4. So number 4, we have 226 on this side, 222 on this side. So what do we have to add over here? What goes the top? What goes the bottom? What element is this? And then what type of decay? Alpha. All right, so on this page, I want y'all to know that this one is alpha. And then this one right here, I know it looks like alpha, but this one is not even decay. This one is fusion. I want you to write them down, and fusion, yes. So the reason I put this one here is because I do want you to know it. So what is the formula for fusion? What's the formula that's going on in the sun? Hydrogen plus hydrogen produce what? That's what's going on for number 7, okay? But for number 6, you're just going to add this side and treat it like it's one thing, okay? Y'all got this. This will take you about 10 minutes to do. Once you're finished with this, I want you to move on to the mock ACP. And once you're done with the mock ACP, that's it. You're done for the day. Please do not waste any time.
If you don't know how to do chemistry, hit that subscribe button. Let's